And so if you look at our data sheets, you've got two different sections here. Down there at the bottom, you see permanent linear change, and you see the permanent linear change based on different temperature ratings, temperature thresholds. So, the permanent linear change at 1500 degrees is not the same as it is at 25. And so as you heat this up, you've got to take into that permanent linear change. And then you also see the box where coefficient of thermal expansion. And that coefficient of thermal expansion, again, is a reversible change. So once it's being heated up once, if you reheat that part, it's going to grow and shrink under that, in that same level of thermal expansion every time, regardless of how many times it happens. So we use those two values to estimate the total thermal expansion. And so, what we're looking at, in this formula, your first term is looking at your reversible thermal expansion, and then your second term is looking at that permanent linear change. And so what we'll do is you can, by combining the total length, the coefficient of thermal expansion, and then your temperature difference, how much you're heating it from ambient to your hot phase temperature, and then you're adding that permanent linear change, gives you the total amount of thermal expansion that needs to be allowed for on the refractory. And then now, if in the case that you're dealing with pre-fired shapes, precast shapes, you don't need to worry about that permanent linear change because that's already occurred. You only need to worry about the reversible thermal expansion. And so if we look at that coefficient of thermal expansion with different materials, typical aluminosilicate refractory, which is the overwhelming majority of what Plibrico supplies, that slope, that coefficient of thermal expansion is pretty linear. And what it tells you is that, in a nutshell, as you heat up the refractory, it grows, and it grows in a very controlled and very predictable fashion. Now, some refractories, if you have a refractory, typically a lower grade refractory, something that contains a lot of quartz, a lot of free silica in it. Quartz has will actually change at about 1073 degrees Fahrenheit, where it stops being quartz and it changes to cristobalite. And when that change happens, the thermal expansion changes a little bit. And if you're dealing with a refractory that has a large amount of quartz in it, typically low to medium duty fire brick, and you're working with it in that range, and you're planning your heat up, you need to be sure to plan for that. Now, other refractories that contain zircon, for instance, they do something even funnier. So zircon goes through some significant crystal changes in crystal structure. And when that happens, it happens at around 2000 to 2200 degrees Fahrenheit when you heat it up. And again, you can get a really strange effect in that expansion coefficient. And then it changes again as you cool it down, but it doesn't happen at the same temperature. So again, understanding the behavior of the different materials that you're working with and being able to predict them effectively is important. Now, fused silica refractories, those are nice. The reason we like those for thermal expansion is because they are relatively flat. They have very close to a 0 thermal expansion coefficient up to about 2000 degrees. And the reason that it's only up to 2000 degrees is that fused silica is essentially high silica glass. And so that high silica glass comes with that very low thermal expansion coefficient. We like to take advantage of that as much as we can. But above about 2000 degrees, that glass starts to crystallize. And that, as it does that, it changes from glass to cristobalite. Now, cristobalite is still a good refractory, but it has a huge thermal expansion coefficient. And so if we extended this line out at 2000 degrees, you would see that coefficient of thermal expansion shoot up, and you would lose all of your thermal shock resistance.